All right, what's going on? Today we're going to be doing a problem called reorder list. It's a linked list problem, so let's get into it. So we're given the head of a singly linked list, where the list can be represented as nodes L0, L1, L2, all the way to Ln minus 1, and then Ln. And they want us to reorder it to be the following form. So they want us to basically alternate between nodes at the end of the list and then the beginning of the list. So L0 to Ln to L1 to Ln minus 1, L2, Ln minus 2, etc., basically till we exhaust all of those list elements. So the even example, or the odd number of list node example, I think is more straightforward. So like if we have this list 1, 2, 3, 4, 5, obviously the node 5 here is going to be the Ln node, so we'd insert that between the 0th and first node. This would be the Ln minus 1 node, and that would get inserted between the 1th node and the 2nd node, so right here. And if you have an even number of elements, obviously you can insert the nth node here between the 0th node and the first node. But then the third node can't go anywhere because obviously there's nowhere valid to insert it. Like we wouldn't want to insert the 3 here because that's just not the pattern that they specified. It needs to be like exactly alternating. So if there's an even number of elements here, the last one will just stay there. So yeah, so let's look at some whiteboarding. So this problem can actually be solved pretty easily with linear time and linear space. Obviously, like I think it's pretty clear, like any solution to this problem is going to have linear time complexity because you're going to have to look at every node to reorder it. It's not as clear what the optimal space is, but naively, you could do this with linear space pretty easily with a stack. So if we had, let me just put an example list here, example list input. So, and by the way, they want us to do this in place, so we're not like returning anything. But yeah, let's just say we had this list. To do this with a stack, you don't want to just traverse through this list with a current pointer and basically just push a pointer to every single node here to a stack. So I'll just draw our imaginary stack down here. So let's see, 1, 2, 3, 4, 5. That's good. So we're going to be pushing every single node there. So obviously the first node would be at the bottom of the stack, and the way the stack data structure works is we're going to keep basically just stacking those pointers on top of each other. So then once we do that, so now we have a stack of all the pointers. We want to just iterate through the size of the list divided by 2 to basically go backwards through this portion of the list and insert them in their corresponding places in this original list. So basically what we do with each loop iteration is we'd take a pointer to this 5. So we'd basically just access the top element of the stack. Also, we'd be pointing to the beginning of the list at first, and we would just pop this from the stack. Now, we can't just move this arrow first because we need to preserve the end of the list. So to do that here, we're just going to point the 5 first. We're just going to point the 5 first to this 2. So now that we have the rest of the list preserved, we can safely repoint this 1 to the 5, and then we just shift this pointer down to the current next node to skip that node we just added. So so this would now be here, and now we're almost done because we only need to loop through half of those list elements, rounded down, if we had like an odd number of elements here. So rounded down, so it would just be these 2 elements. So now we'd have node 4, we got a pointer to that. We pop it from the stack, and we want to insert it here. So just to indicate that that's been popped, cross it out. And we just want to point this 4 here to preserve the rest of this. Then we can cut this link here, or not cut it, but just repoint it to this 4, and then slide this down. And now we're done because we've already looped as many times as we need to. So we can just notice though we're not completely done. We're done looping, but we're gonna have to set this 3 to a null pointer because we created a loop here. So we'll just set the 3 to a null pointer, and at that point we're done. And there's no memory leaks by doing that. It looks like we just cut off the list, but we still have access to all of these nodes here, so we didn't lose anything, and we just return a pointer to this first element. So again, that's going to be linear space for the stack, and then I'll just show that the code here. So we're going to have a stack of list node pointers. I'll just call that st. We're also going to have a pointer to the current node to add all of those nodes to the stack. So we'll just say while cur is not null pointer, we can basically just use the push method to push that current node pointer to the stack, and then shift the current node down the list. That's pretty much it to get all those nodes in the stack. We're going to need to set the current node pointer back to the head, right? Because we want to restart at the beginning of the list for this next portion of the algorithm. We also need half the size of the list. So to get that, we can just use the size of the stack. So constant, I'll just say half size. We can take the size method on the stack and just divide that by 2. And then we can loop while we'll have a variable called I, we'll increment it, and we'll just do that while it's less than half size for the proper number of iterations. And then we can take a list node from the top of the stack, and I'll just call this stack node. So we'll just take that top element from the stack, and then we can just pop that because we have a pointer to it now, but we don't need it in the stack anymore. So we're going to take that stack node, whatever so it needs to point next to the whatever the current node is pointing to next, right, to preserve the rest of that list. And then the current next can just get set to point to the stack node. So what we just did is pointed this node. So like if we were at the 5, we popped it from the stack, we pointed it to the rest of the list, and then we pointed this first element to the 5. And then we would just want to move the current pointer in the list to current next to skip the node we just added. So the final part of the loop will just be shifting that current pointer down to the next node. And then after all of that, remember, we would still have a sort of loop thing here that we created. So the 3 would point back to the 4, but obviously we don't want that. We just want the list to end there. So we're going to point current next to null pointer just to cut that list off at the end. And then we can just return because we did that in place, so we don't have to return anything. So that's pretty much it for the linear space solution. So let's see what's going on with this. So right, this current node should have been head at first. So let's run that again. So as you can see, the runtime is very good, but we can do better on memory. We're not doing very good on memory. So we can actually do this with constant space. We don't really need to use a stack. So let's go through that version of the solution. It's slightly more optimal, a little more confusing, but it's more optimal. So I just want to delete this whole page here. So we'll look at the same example. So we have just a list of list nodes, 5 list nodes here. So the idea here is going to be, like, if you noticed, for these, the reason we use a stack is because it basically allowed us to go through the end of the list in reverse order, like, very easily. But we can actually just basically cut these into 2 lists, reverse this second portion of the list, and then insert it. Basically just like merge them together. So really there's like 3 phases of this algorithm. It's like, first we need to find where the second half of the list starts, right? Because like we can't really do that in constant time with a linked list. We're gonna have to traverse it first to figure out, where the second half starts. Then we need to basically separate this list into 2 lists, where this part of the list, we need to reverse it. So we need to reverse the linked list on this part. Then we can merge them. So I'll show the algorithm for each portion. So the first portion, when we're gonna find the middle of the list, we'll just use a slow and a fast pointer. So this is pretty standard for finding the middle of a list. So our slow pointer will be starting at the head of the list at first. Our fast pointer will be starting at the next node, and then basically with each iteration, our slow pointer will shift down the list by 1 node, and our fast pointer will shift down the list by 2 nodes. And then we're going to keep doing that while fast is not null, and then fast next is also not null. So I'll just show what that would look like. So the first iteration is going to look like that, and then we would move. Once the fast pointer gets here, obviously it's null, so we'd be done looping at that point, and we would have found the center, which would just be not slow, but slow dot next, right? Because that's going to be the second half we're looking to reverse. So now that we've done that, we could basically just reverse the linked list on this portion of the list. I have a video for reversing a linked list, so if you don't know how to do that already, I would check that video out. But once we have reversed the linked list, we're basically going to want to merge those 2 lists together. Also, this 3, once we're done reversing the linked list, or basically once we're done with this pointer, we can safely set this 3 to null instead of 4, right? Because we want these to be like 2 separate lists. So so now I'll show the algorithm where we merge these. So we're gonna have this first list here. I'll just say this is the first list, and then we're gonna have our second list here, which is reversed. So it'll start with a 5, and then there will be a 4, and then that'll point to null. So now we need to merge these, right? So to do that, we're gonna have to have 2 temporary pointers, list node pointers, just to preserve the rest of both of these lists while we're merging them, essentially. So we're gonna have a pointer for, which we'll just call next, for this list, and then for the next list, or the other list, I'll call it next 2. So at first, so the first thing we're going to do with each iteration of the loop where we merge these is basically just set. So like we're going to be here at first on this list, and we're going to be here at first on the second list. And so obviously next there's going to be 2. So we have a pointer there preserving the rest of that list, and then next here on this list will be 4. So basically what we want to do first is set the next value of whatever the head is on this first list to the head of the second list, right? So because we've already preserved this with this pointer here, so we can remove this link and then basically just point it this way, right? And then what we can do is we've also preserved this second list here, so we can just point this head 2 on the second list to the next pointer on the first list. So this would now look like this. And then we're going to slide both of these pointers down to these nodes that we preserved. So this and this would now be this and this. So now we can do the same thing again. So this 2 is going to, we can safely remove this link. Well, first, let's make sure we update these. So the next on the first list would now be 3, and then the next on second list would be 4. So now we can move this pointer here. This one can get repointed to this, and now we can just shift those pointers down again. So, and we're just gonna loop while the head of the second list is non-null. So at this point, it would be null, so we'd be done looping. And as you can see, this is the answer they're looking for. So we would just return a pointer to this first element. Actually, we're not returning a pointer. Never mind. This is in place, so disregard that. But we would just return void there. So, and we've done this in place, and it looks correct. So let's go ahead and get into the code for the optimal constant space solution. So let's reset this. So this time we're not going to use a stack. So we're going to use a slow and a fast pointer basically to, so we're going to have a list node, we're going to have a slow pointer, and that'll just be pointed to the head. And we also need a pointer for a list node that we'll call our fast pointer. That'll be head next. And then we're just gonna loop while fast is not null and fast next is also not null. And we'll just shift the slow pointer down the list by 1 and the fast pointer down the list by 2. Okay, and then once we've done that, we know that the middle of the list is going to be slow dot next. So we can call our slow arrow operator next, right? So list node, we'll just say head 2 because that'll be the head of the next part of our list, but it hasn't been reversed yet, but it'll be slow next, right? So, and then we can break those two lists apart and separate them by setting slow next to null pointer, because we've already used that to find the middle there, so we're done with it. Then we break them apart. We need so now we're just going to reverse that second half like we would reverse a linked list normally. So we need a previous pointer that can just be null at first. We also need a next pointer that can also be null. So we're just going to loop while head 2 is not null. And we're just going to, at first we want to set the next node to be head 2 next, right, to preserve the rest of the list. Then we can point head 2 next to basically whatever the previous element was, and the first iteration it'll be null. That's fine, because that'll be the end of the reversed linked list. So then we can shift the previous pointer in the head down the list. So so the previous pointer will just become the what the head was before, and then the head will become the next whatever the next pointer was pointing to. So and that was head2.next. So that's reversing the linked list. Obviously, for this algorithm for reversing a linked list, our new head of the reverse linked list will be stored in the previous pointer at the end of this looping. So with that in mind, we're going to set head2 just back to that previous pointer, so that points to the beginning of our reversed linked list for that second portion of the list. So yeah, so now we have two lists where head is pointing to the beginning of the first one, and then head2 is pointing to the head of our reversed list, the second portion of the list. So now we need to merge these lists together. So we need two pointers, right, to preserve the ends of both of these lists while we're merging them. So I'm just going to recycle the next list node for the first list. So that'll just be, I'll just set these null pointer at first before we start looping. So next will be null pointer, and I also want a list node to keep track of the rest of the other list. So we'll just call this next2. That'll also be null pointer. And then we're going to loop while head2 is not null. And we're basically going to first want to preserve the end of both lists. So next will be head next, and then next2 will be head2 next. Now, so the next thing we want to do is basically set head next to whatever head2 was, because we're basically, if you remember, we want to set this variable, or basically we want to set this variable to this one first. That's what we just did. And then we want to set this node, the next node, we want to point this node to the next one from the first list. So to do that, we're just going to say head2 next equals, that's going to just be next, right? Because we preserved that here. And then after that, we can just basically shift our nodes down the list. So our head nodes down the list. So the head we can just point that to next, right? And then we can do the exact same thing for the other list, but with its respective dummy pointer there. So so that's pretty much it for the constant time solution. We can just return after that, because remember, we did this in place. So let me just go ahead and run this. So yeah, so as you can see, this is going to bounce around. I mean, this is probably about the same time as the first one if you ran this a few times, but the memory is a lot better. So we did a lot better on the memory there because we're using constant space now instead of linear space. So hopefully this video helped you understand this problem more. If it did, leave a like and subscribe, and I'll see you guys in the next piece.